Hey everyone, it's Miss B, and in this video we're looking at the Algebra 1, Unit 5, Lesson 3 practice problems. So, first off here we have which expression is equal to 4 to the power of 0 times 4 to the power of 2. So, anything to the power of 0 is just 1. So this is going to be 1 times, and then 4 squared would be 4 times itself 2 times. So in this case, 1 times 4 times 4 is going to be 16. Now there's a more complicated reason as to why 4 to the power of 0 is 1, but we're using that property here. For question 2, we want to select all expressions that are equivalent to 3 to the power of 8. So first of all, 8 to the power of 3 is not the same thing, because 3 to the power of 8 is 3 multiplied with itself 8 times. So that's also not going to be 3 times 8. That's a very basic description of it. But now let's look at all of the rest. If we have 3 to the 10th divided by 3 squared, with exponents, when we divide, we actually subtract our exponent numbers and leave our base the same. So this would be the same as 3 to the 10 minus 2, which is, yes, the same as 3 to the power of 8. If we look at option D, when we have exponents raised to another exponent, we actually multiply them. So this would be the same as 3 to the 4 times 2 for the exponent. And yeah, 4 times 2 gives us 8. So this is also equivalent. When we look at E, this is 3 times 3, then raised to the power of 4. And we could multiply the 3's inside and make this 3, or make this 9 to the power of 4, but that doesn't help us with our explanation here. So what I'm actually going to do is write those inside as 3 to the power of 2, because I have 3 multiplied with itself twice, and put a 4 on the outside, the same place it was, so it doesn't move. And now this question is just like the one above it. We're going to multiply, and this would be 3 to the power of 2 times 4. And so again, yes, this one is equivalent to 3 to the power of 8. Now for part F, we have 1 over 3 to the power of negative 8. So this one is also going to be equivalent. The short explanation is that anytime you have a negative exponent, you will change whichever side of the fraction it is on. So we could just jump straight to moving 3 to the negative 8 up into the numerator. Our other way of thinking about this is that 1 is the same as any number to the power of 0. So we could say this is 3 to the power of 0, and then minus negative 8, because the division sign means we subtract. That is going to be the same thing as 3 to the power of 8, so it works. I like to also just think about it as anytime it has a negative, you move it to the top. But there are 2 ways to think about that question. So B, D, E, and F are all equivalent to 3 to the power of 8. Moving to question 3, we have a bee population, and it's measured each week, and the results are plotted on this graph. So the first question is, what is the bee population when it is first measured? And so for us, that is this right here. It is our vertical intercept. And the vertical intercept is our initial value. And here it looks like it is 500. So I'm going to just write 500. Question B says, is the bee population growing by the same factor each week? And explain how you know. So if we look at what our numbers are, that first week looks like it's 500. Then, so I would have like 500, and then it goes to 1,000, And then, oops, wasn't very clear, 1,000. And the next week, yeah, so here we're at 1,000, here we're at 2,000, and then we're at 4,000. So it absolutely looks like it is growing by the same factor. So yes, it is growing by a factor of 2. And my explanation for how I know is that I'm showing the numbers going from 500 to 1,000 to 2,000 to 4,000. Because that's what I did in order to check it. So part C says, what is an equation that models the bee population, which we're going to represent with B, W weeks after it is first measured? So we want to represent the bee population. So we're going to say B is equal to. Or we could say B of W if you really want. So you could say B is equal to or B of W if we're putting this in function notation. Now we want to start with the initial value or the initial bee population, which is not 1,000, it is 500. And then that 500 is going to get multiplied by whatever that growth factor is, right? It's growing by a factor. So that is our growth factor, and that is 2. And it is getting multiplied by that each week. So our variable goes in the exponent here. And that equation, we can say or, if you don't want to use function notation, we can say or just B is equal to, both of these would be correct, 500 times 2 to the power of W. But yeah. Let's look at question 4. So a bond is initially bought for $250. It doubles in value every decade. So we're going to first complete the table. So decades since the bond is bought, that's the initial value. At 0, it is going to be $250. Now, after 1 decade, that's going to increase or multiply by 2, so 500. If we double that again, we will get 1,000. Doubling that, we get 2,000. And now D is just the decades. So we're actually going to finish this table as we kind of write our expression. But when they give you just a general variable right here, they want you to write what your pattern is or what you've been doing each time in the space to the right. So what I was doing is taking 250 and multiplying it by 2 for however many times a decade occurred. So since exponents tell us how many times we are multiplying something, that is going to tell me how many times I would take it and multiply it by 2. So that actually is going to help us out with the rest of this question. So first is then, how many decades does it take before it is worth more than $10,000? So I'm actually just going to write out a little bit more of my table because I'm not too far off. I ended at 2,000. So 2,000 would then go to 4,000, which would then go to 8,000, which is almost 10, but not quite, and then 16,000 after that. So this was going to be decades 4, 5, and 6. I would say 6 decades is my answer. Because at 5, it is still not quite at 10,000. So part C asks us to write an equation relating V, the value, to D, the number of decades. And that is where my expression right here, because this doesn't have an equal sign, so it's an expression. We're going to change that into an equation. So we can either say V is equal to And we're just going to use that. We're going to use 250 times 2 to the power of d, or you could write it as v of d if we're using function notation. So I'll put or is the same thing, 250 times 2 to the power of d, because d is our input. Whoops. Accidentally minimized it there. I was trying to swipe a hair off of my screen. Okay, so let's keep going. Question 5, I'll zoom out here. A sea turtle population, so P is the population, that's modeled by the equation P equals 400 times 5 over 4 to the power of y, where y is the number of years since it was first measured. So y is the number of years, and turtle population P. And then they give us this equation, so I'm going to highlight my equation here. It seems pretty important. How many sea turtles are in the population when it is first measured? So that is asking, hey, what is the initial value of this turtle population? And that is going to be 400. And we can say this is, and it's kind of our first number here, right? It's just right in front of our growth factor and our exponent. So we're going to use the formal mathematical language and say this is the coefficient on or of coefficient. We can say the coefficient in next to, or the coefficient of the growth factor and the growth factor is the number raised to the exponent. Or you could really just say like 400 times this to the power of y, it was 5 over 4. Then we can highlight this and say right there. Okay, so now we want to know, is the population increasing or decreasing? And how can we tell from the equation? So the 400 is the original amount of turtles in this population. We can tell if this is increasing or decreasing by looking at the growth factor. So if our growth factor, and in this case our growth factor is the 5 over 4, right? The growth factor is that number that's raised to the exponent. If that number is larger than 1, it is going to be growing or increasing. And so 5 over 4, since that's an improper fraction, there's a larger number on top than there is on the bottom, then yes, this is absolutely going to be increasing. So increasing. I can tell because the growth factor is greater than 1. So when will a turtle population reach 700? And explain how you know. So I am actually going to use a calculator to check these answers, or to check my numbers as we go. You can also use a graphing calculator to look at your graph of this. So I'm just going to use a scientific calculator and plug in some numbers here until I find the actual amount. So let's say 400. I'm going to multiply that by 5 over 4. I know you can't see what I'm doing, but I just want to explain as I go what I'm looking at. So I'm putting 5 over 4, and then I'm just going to try raising this to different exponent values. So first I'm going to try after 1 year and just see what that is. Well, that's 500. So if I try 5 years, I'm at 1,220. So they grow pretty fast. So let's try 2 years. 2 years shows me 625, which I think means that after 3 years, I might actually have the right amount here. Yeah, so when will it reach 700? So I'm going to say 3, and this was y is the number of years, so it will reach 700. Now, at 3 years, after 3 years, it will be more than 700, and at 2 years, it will be less. So it will reach 700 between the second and third year. And I would explain how I know by saying 400, and I'm just going to show the math I did. To the power of 3 was 781.25, and then 400 times 5 over 4 to the power of 2. This was, I believe it was 625. Yeah, 625. And so that's how I checked. So that's my explanation. Now we're on to some review questions. So bank account A starts with $5,000 and grows by 1,000 each week. And bank account B starts with $1 and doubles each week. So which account has more money after 1 week and after 2 weeks? Well, they're actually giving us a graph down below. So you can either evaluate by checking or by just looking at your graph. After 1 week and after 2 weeks, we have the two accounts here. The account that started with more money in those first, 1 week and 2 week is right here. It is still the account that started with more money. So bank account A will be the one with more money in both of those cases. Account A for both 1 and 2 weeks. Okay. Here's a graph. Which graph corresponds to the situation, and explain how you know? Well, I kind of did that in my head in order to read from this, but account A is going to be the one that starts with more money and then increases by a consistent amount, meaning it's a linear function. It's increasing by the same amount each time. And then bank account B, that's going to be the one that has a small amount, but is going to grow exponentially and have this curve. So we'll say A is triangles because it increases at a constant rate. And then I'm going to say B is circles because it increases exponentially. Okay. And yeah, I know I was writing on the edge of my page, so I was trying not to try to cram my handwriting too much, but they don't give a ton of space for answering that question. I guess I could have written it on the left side. So given a choice, which would you choose, and explain your reasoning? I might choose account B if I am a patient person and I can wait more then what is this? This is 14 weeks. If I can wait more than 15 weeks, which is like 3 or 4 months, 3 months would be 12 weeks. So if I can wait almost, 4 months, then yeah, I would want account B to hang on to. So I would say account B. B, it will have more money eventually. And we can say this is after 14 weeks. Because at 14 weeks, still going to be less, but after 14 weeks, it's going to increase. Okay, and then that should be it. Oh, no, we have one more question here. Sorry, thought that was the last one, but it's not. We have one last question. Function f is defined so that its output, which is f of t, is the number of followers on a social media account t number of days after the account is set up. So we want to explain what f of 30 equals 8,950 is in this situation. So this is our function value, f of 30, right? It says f of t is the output. It's the number of followers. And they're saying f of 30 is 8,950. So this to me says the number of followers after 30 days is 8,950. So yeah, that's what we're going to write. The number of followers after 30 days is 8,950. Explain the meaning of f of 0 equals 0. Well, we're going to translate this the same way. The number of followers after 0 days, meaning the day it gets set up, is 0. So that's your original amount of followers. The number of followers we can say when the account is created is 0, which makes sense. When you create an account, you don't have any followers at first. You have to add people and hope they add you back. So now we're going to write a statement about function f that represents the fact that there were 28,800 followers 110 days after the setup. Well, that's now just asking us to do the opposite. Instead of explaining the function notation, we're now going to explain this sentence written in words, and we're going to put it in function notation. So we're going to say f, and then in the parentheses goes our number of days. So the number of followers after 110 days is equal to, in this case, excuse me, 28,800. Explain the meaning of t in the equation f of t equals 100,000. Well, t in the original function is t days after setup of the account. So in this case, they're asking us how many days after the account is set up will it have 100,000 followers? So we would say t would represent the number of days after the account is created that it would take to reach 100,000 followers. Ta-da! So now that should be our last one because, yep, just took a peek. My next assignment is for lesson 4. So this was everything for Unit 5, Lesson 3 of Illustrative Math, Algebra 1.